Hello, this is Ms. DB. In today's lesson, we're going to learn about exponential and logarithmic equations and how to solve them. This is from Chapter 7, Section 5 of your book, and we're not going to do the inequalities in this lesson. So an exponential equation is an equation that has one or more expressions that have a variable as an exponent. There's two ways to solve exponential equations. The first method is to try writing the two different sides of the equation so that the bases are the same. Because if you have the same base, then the exponents will be equal. Or the second method is to take the logarithm of both sides. And that way you'll be able to use the properties of logs in order to find the answer. If you use a rounded number when you're checking, your result will not be exact, but it should be very close. So when you round a number in math, use as many digits in the decimal as you can. At least for logarithms, use at least 3 digits after the decimal. If you can, instead of rounding, use the whole number by saving it on your calculator and then just doing the whole calculation on your calculator. All right, let's look at how to do these problems. We'll try both methods, and sometimes both methods will work. Sometimes the first method doesn't work and you can't rewrite them with bases, and then you have to take the log of both sides. But in this one, we have 9 as the base on one side and 27 as the base on the other side. Now, because we're solving an equation, we're looking for the value of x here. So the way that we're going to try first is see if we can rewrite 9 and 27 with the same base. And we can, because they're both powers of 3. 9 is 3 squared, and 27 is 3 cubed, 3 to the third power. So we rewrite both 9 and 27 as a power with a base of 3. After that, then we can simplify both sides. So on the left side, we have 2 times 8 minus x. That's 16 minus 2x, because 2 times 8 is 16, and then 2 times x is 2x. On the right side, we have 3x minus 3 times 3 is 9. So we did the distributive property for the exponent part. Next thing we have, this is 3 to the 16 minus 2x, and this is 3 to the 3x minus 9. If you have the same base, that means their exponents are equal. So now we can just write the exponent part. 16 minus 2x equals 3x minus 9. Now from there on out, it's the same as solving for x way back to, probably pre-algebra you did this. They're not showing all of the steps, but we would add 2x to both sides, and we would get 16 equals 5x minus 9. Add 9 to both sides, and we would get 25 equals 5x. And that's how they got their answer of x equals 5. 25 divided by 5 is 5. Now you should check these as well. Sometimes your answer won't work. These are kind of complicated looking equations. So we want to take our answer of 5, which is what we got, and plug it back into both sides of the equation and see if we get a true statement. So if you plug it into the left side, you get 8 minus 5 is 3. 9 to the third power is 729. On the right side, we would have 5 minus 3 is 2, so we have 27 squared, and it happens that 27 squared is also equal to 729. So this answer does work. All right, let's look at this one. All right, 4 could be written as 2 squared. That's about it. But 5 cannot be written as a power of 2. There's no way to write these with the same base, so we're going to try method number 2, which is to take the log of both sides. That means that you just write log in front of both parts. Now this would be log base 10. We're using the common log. You don't have to write the base 10 if you're using the common log. That's why we use it. Then we can just write log. It's a lot easier. You could use any base, but we're going to use log of 10, which is the common log. All right, so now we have the log of 4 to the x minus 1 equals the log of 5. Now we can use our properties of logarithms that we learned about. And one of those was the power property of logarithms, which says that if you have the log of some number that's raised to a power, you can take that power and put it out front. We learned this in section 4. So x minus 1 times log of 4 equals log of 5. Now you can work with this log of 4 is 1 unit, and this log of 5 is 1 unit. You can work with them just like if they were numbers or variables, and we can divide both sides by the log of 4. That came up a little bit quick. So I can divide both sides by the log of 4. What that does is it cancels it over here, and I'll be left with x minus 1 is equal to log of 5 over log of 4. Now when you get down to this part, you have to get your calculator out and take the log of 5 divided by the log of 4. And then you'll take 1 plus that. So when you take the log of 5 divided by the log of 4 on your calculator, you should get about 1.161, and then you add 1 to it, and it's about 2.161. Now there's more decimals after that, but this should give a good approximation. We went out to 3 decimal points. Now when we check this answer, we might not get exactly that this side is equal to 5. So if I take 2.161, plug it back into for x, and then subtract 1, I'd get 1.161. So I'm really saying what is 4 to the 1.161. And if I do that on my calculator, I get 5.0002491. Very, very close. Close enough for me to say, yes, this is good, it's correct. All right, so here, let's check this one. Can you rewrite both of those, the 3 and the 27, with the same base? If you can, then you might want to try that method first. So in this one, I could rewrite, well, the 3 is done, 3 to the 2x, but on the other side, I could write 27 is 3 cubed. And then look how quick this is going to be. Because we have the same base, the exponents are equal to each other. I don't know why that step had to be included because there was really nothing to do there, but so we have 2x equals 3. Our answer is 3/2 or 1.5. And you can plug that back in here, check it, and that's going to check really fast because 2 times 1.5 is 3. 3 cubed is 27. It checks. All right, how about this one? Can we write both of these to the same base? Now you might think 21, yeah, that's 3 times 7. That'll work, but it won't because there's no way to write 21 as 7 to some exponent. 7 to the first, of course, is that 7 squared is already up to 49. So we cannot rewrite 21 as a base of 7. So we're going to take the log of both sides instead. So you just write log in front of both sides. Then you do your power property, which says you can take this property or this exponent and put it out front, this power, I mean. So we have negative x times the log of 7 equals log of 21. Now we can treat these the same as if they were any other expression. We can divide both sides by log of 7. Don't think that this is log of 3. It doesn't work that way. So we have negative x equals the log of 21 over the log of 7. You need to get your calculator out. Let's see if I can find my calculator here. On my computer, log of, here it is. So on my calculator, which is not exactly the same way a handheld one would work, I would take 21 log, and now I'm not going to write that down, 1.322222. You could, but I'm going to instead leave it on my calculator and write divided by, and then I'll use my parentheses to type in log of 7. Log. And then I'll close my parentheses. So I have the log of 21 divided by the log of 7. That's exactly what I wanted. Hit equal 1.56457 ... And then it was negative, so I have to put a negative in front of that. Don't forget that. Okay, so negative 1.565. You can check it by plugging that back in here, and you should get something very close to 21. It's a little bit off, but that's okay. All right, these are the problems from your worksheet. Now, I'm not going to do number 1 because I have step-by-step solutions laid out for you to go through method 1 and method 2. I just want to point out that there are things you have to finish on here towards the bottom, and you should actually read through the steps, and as you're doing your other problems, you can come back here as needed to review how to do both methods with this problem. All right, then on the next few problems, let's see, number 2 is started for you. On this one, I took the log of both sides, and then I wrote log of 3 to the 4x equals log of 90. And so far I've used the power property to put the 4x in front. Now this is very similar to what we just did on the last example. Now you would divide both sides by the log of 3, and then you're going to have to get your calculator out, because 4x will be equal to whatever the log of 90 divided by the log of 3 is. That's not log of 30, don't do that. So you find out what it is, and then you'll have to divide your answer by 4, because that's what 4x will be equal to, and you won't be done yet. Let's look at number, I don't know. It looks like number 5 has a typo in it, so I'll make sure that that's not there when you get your worksheet. Let's look at number 3. So we have 5 to the x minus 3 equals 600. Now you might be thinking, can't I rewrite that as a power of 5? But I know that 5 squared is 25. This might be a good way to find out. I know that 5 cubed is 125. And I know that 5 to the 4th is 625. So there's no way to rewrite 600 with a 5 as a base. So that's not going to work. Let's look at number 6. In number 6, I have, so you're going to have to take the log of both sides. Log of 5 to the x minus 3 equals log of 600, and then you'll finish it a lot the same as number 2. Actually, all 3 of these will be very similar to number 2. But in number 6, it's a little bit different. We have 1 over 32 to the 2x, and that is equal to 64. And there's a hint that 2 to the negative 4 is equal to 1 over 32. So I can rewrite the base on the left as 2 to the negative 4, and then that is to the 2x power. And that is going to be equal to 64, but I want to write that with the base of 2 as well. So let's see, I know 2 to the 4th is 32, right? Let me just double check this. 2, yep, that's 2 squared is 4, 2 cubed is 8. 2 to the 4th is 16, so this should say 2 to the 5th. 2 to the 4th is 16, 2 to the 5th is 32. So I have to write this as 2 to the negative 5th, and then 2 to the 6th would be 64. So this will be equal to 2 to the 6th. So now we have the same base on both sides. They're both the base of 2. I'll simplify the left side so that I have 2 to the negative 5 times 2x would be negative 10x. And on this side, it's still 2 to the 6th. And now I can say that the exponents are going to be equal to each other. So negative 10x equals 6. And x would be equal to a negative, let's see, 2 goes into both of them, negative 3/5. All right, here's an application problem. Suppose a bacteria culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1 million? So at hour 0, there's 1. So we're starting at 1. Or that's the same as 2 to the 0. At hour 1, after 1 hour, there are 2, or 2 to the 1, and so on. So at hour n, there will be 2 to the n. All right, that makes sense. So we're going to write 1 million in scientific annotation. So we want to solve when will 2 to the nth be greater than 10 to the 6th. So we use scientific notation to write this as 10 to the 6th. There's 1, 2, 3, 4, 5, 6. Yep, okay. Now, I can't write 10 as a base of 2. So instead I'll take the log of both sides. And my question is, when will the log of 2 to the nth be greater than the log of 10 to the 6th? So we'll use the power property of logarithms to put the n in front. So we have n. Oh, and then on this side, log base 10 of 10 to the 6th is just plain old 6, because this is base 10 and this is 10. So now we have that the n times log of 2 is greater than 6. So all we need to do now is divide both sides by the log of 2, and then get your calculator out, and we will find that n is greater than about 20. It'll take about 20 hours for the number of bacteria to exceed 1 million, maybe just a little bit less. And that's, yep, we can see that if we plug 20 back in, that'll be more than 1 million, so our number of 20 is just a little bit high, but it's very close. All right, let's look at how to solve logarithmic equations. So we looked at exponential equations, now we're going to look at log equations. A log equation is an equation with a log expression that contains a variable. You can solve these by using the properties of logarithms. So if the log base b of x equals the log base b of y, then x equals y. So if these two parts are exactly the same, then these two parts are exactly the same. You can look back at your worksheet and in your book as you need to on this section to review some of the things that we learned in 7.4, because there was a lot. And in 7.3 we learned the definition of logs and how to write exponentials as logs and logs as exponentials. You'll want to remember that. Remember the product property that says you can change a multiplication into addition, or it works the other way too, an addition into multiplication. And the quotient property, that if you have division, you can write it as subtraction or subtraction as division. And then the power property we've already used today. If you have the log of a power is the product of the exponent and the log of the base. There's a couple more on this page. The inverse properties, we just used this one. And it works for the logs as well. If you have 10 raised to a log and that has a base of 10 as well, then it's just equal to that number right there, the 2. And then the change of base formula, we might need that. I don't think we'll need it in this lesson, but it's a good thing to review. All right, so here we have an equation that has a log in it. So let's look at how we could solve this problem. First of all, we are going to make both of these parts of this equation as the exponents to the base of 6. Now, why did I pick 6? I picked 6 because it matches this. So I'm raising both sides, turning them into exponents with the base of 6. The reason I did that again is because now on this side, it's an inverse property. 6 raised to the log base 6 will just be this number. So I don't have that anymore. On the left side, 6 to the negative 1, that's the same as 1/6. So I simplified that way as well. So now I just have an equation. I took this complicated thing and I turned it into 2x minus 1 equals 1 to the 6th. Then you just add 1 to both sides, divide by 2, and you'll have your answer. This is 1 and 1/6, which I think I'll write as 7/6. And then I will divide by 2, which is the same as multiplying by 1/2. So I'll get x equals 7/12 as my answer. All right, here's another example. We have log base 4 of 100 minus log base 4 of x plus 1. They're both base 4. It's a subtraction, which, let me see if I can go back quick to the quotient. Look at the quotient property. If I'm subtracting and I have the same base, I could write that as log base b of m over n, which is very similar to what we're going to do for this problem. We're going to write this as log base 4 of 100 over x plus 1 equals 1. Now I'm not done yet, but I got that far. I got it simplified. Now I can raise both sides with 4 being my base. I'm turning both parts into the exponent with 4 as the base. And I'm using 4 because this problem, the step right above it, had 4 for the base of the log. So on the left side, 4 raised to the exponent log base 4 is just going to be 100 over x plus 1. And 4 to the 1 is just 4. So we have 100 over x plus 1 equals 4. Now to solve this, this is not something you normally would solve in algebra with the x plus 1 on the bottom. But we would multiply both sides by x plus 1 to get it out of the denominator. So I would have 100 equals 4 times x plus 1, or 100 equals 4x plus 4, so 96 equals 4x, and then I have to divide that by 4, 96, so 24. So I get that x is equal to 24. So once you get rid of the log part, you still have to solve the equation correctly. So try to do that to the best of your ability. This is number 10 on the worksheet. So number 10 on the worksheet says that we have log base 4 of x to the 5th equals 20. So what we want to do is first put the 5 in front using the power property. So I have 5 log base 4 of x equals 20. So I use the power property. Now I can divide both sides by 5. Did that. Divide by 5, divide by 5. I get log base 4 of x equals 4. Now I don't have to raise both sides with 4, because I can now, this is simple enough now that you can use the definition of a logarithm, where this is your b, remember. This is your exponent over here, and this is your a. And it gets rewritten as the exponent here, this x part is here, so we'll point that there. And the base is right here, and that's what this is equal to. So use your definitional logarithm, and you can rewrite this as x equals 4 to the 4th, and then 4 to the 4th is just 256. You could raise both of these to the 4th power as well, because then you'd have 4 to the log base 4 of x. That's just x. 4 to the 4th, and you'd have it that way too. So you can either use definitional logarithm, or you can raise both sides to the same number. All right, here's another example. We have this looks long and hard, but it really isn't. We have log base 12 of x plus log base 12 of x plus 1 equals 1. So we have the same base, and there's something, they're being added. The two logs are being added. Well, we can rewrite this as a product, as x times x plus 1. And when we do that, we're going to get x times x is x squared. So this actually is going to turn out to be a little bit longer, because we might get two answers here. So now I'm raising both parts. I'm putting 12 under them, turning them into my exponent. So I have 12 to the log base 12 of x to the times x plus 1 equals 12 to the 1. And that simplifies using the inverse properties as x times x plus 1 equals 12. Then you need to distribute through the x, so we'd have x squared plus x, and then minus 12 from both sides to set this equal to 0. Now we can try and factor this. I think it will factor, like we did in the quadratic functions chapter. So we factor this into x minus 3 times x plus 4 equals 0. So we will get two answers, either x minus 3 equals 0 or x plus 4 equals 0, which means either x equals 3 or x equals negative 4. We have two possible answers. Don't stop there and say that there's two answers. One of them may not work. So when we put those back in and check, here over here is when we check 3. So when we check 3, we get log base 12 of 3 plus log base 12 of 3 plus 1. So that's 4. And then the product property says that I can multiply these two together and have 12. And log base 12 of 12 is just 1. That's an inverse property. On the other side, we have log base 12 of negative 4. But there is no such thing as a negative when you're talking about logs. You can try it on your calculator, you get an error message. So at this point right here, we stop, and we cannot have this as an answer. It is not a solution. So only x equals 3 is a solution. We had to toss one out. Now that doesn't mean that anytime you get a negative, it'll be wrong. It's only wrong if it has to be, if the log has to be of a negative number, then it won't work. Okay, look at this example. We have 3 equals log of 8 plus 3 log of x. Those are the same base because they're both base 10. Even though they don't write that. Remember, that's the common log. So we can use the power property the opposite way than we did before. We can take this 3 and use it as an exponent on the x. That way we can now combine these two parts as a product. We're using the product property. So now we have 3 equals the log of 8 to the x, or 8x to the third. Now at this point you could either use the definition of logarithms and rewrite this in exponential form, or you could take both sides to the power of 10 because this is a base 10, or 10 to that power. Use these as the exponents. So we have 10 to the third equals 10 to the log of 8x cubed. And this, remember, is base 10 as well. So that leaves us with 10 cubed, or 1,000, equals 8x cubed. And then we divide both sides by 8, which is 125. And then 125 equals x cubed. You might recognize this as 5 cubed equals x cubed. So 5 is going to be our answer here, because 5 cubed is equal to 125. Okay, here's number 13 on your worksheet. The problem is right here. Log of x squared minus log of 4 equals 0. And I use the power property to write that as 2 log of x minus log of 4 equals 0. Now it's a minus, and they're both log. The 2 is just written in front. And I have 2 log of x over 4. Which is, then we will raise both parts with 10 as their base, because this is base 10. And I would have 2 times x over 4 equals 1. And that's the same as, let's see, they go for the answers so quick. So that's the same as 2x over 4 equals 1. I will simplify that to 1/2 x equals 1. And then multiply both sides by 2. And we get x equals 2. And then check it by plugging back in, and we would have log of 2 squared is 4 minus log of 4. And you can see that that would be equal to 0. Log of 4 minus log of 4 will be equal to 0. And then here's another reminder to check your answers and watch for possible no solutions. Or if you get 2 answers, one of them may not be correct. These are the problems on your worksheet. We already did some of them. You'll see that number 7 is already started. I already used the power property and put the 4 in front. And then I divided both sides by 4. So then you would have log base 3 of x equals 2. At that point, you can use the definition to rewrite that in exponential form to solve for x. That's maybe what I would do. Or you could take both of these and use 3 as the base and write them as the exponent. And then you would have x equals 3 squared. I'll let you finish that. Number 9. Let's see, this is going to be a quotient one, because it's minus, so we can use the property. They're both the same base, so we could write this as the log of 75x over 3 equals 1. This is log base 10. And then you could use 10 as the base and have these as the exponent. And you would have 75x over 3 equals 10 to the 1 is 10. I'll multiply both sides by 3 to get rid of 3 in the denominator. 75x equals 30, and then finish that up. You'll get a decimal answer there. And then here's the problems, the rest of the worksheet. We already did number 13. Number 12, let's look at number 12. You could subtract log of 2x minus 7 so that it's equal to 0. Let's try that. log of x plus 9 minus log of 2x minus 7 equals 0. And then I could write this as the quotient rule tells me that I could write this as x plus 9 over 2x minus 7 equals 0. And then I could use those as the exponents if this is base 10. So I can take 10 as my base on both sides. And I'd have x plus 9 over 2x minus 7 equals 10 to the 0. Anything to the 0 power is 1. This is one that you better check your answer when you're done. When you have x in the denominator, you always want to make sure that you don't get an answer that would, make you get 0 in the denominator, which is not allowed. So I'd have, x plus 9 equals 2x minus 7. I'll subtract x. So 9 equals x minus 7. So I get 16. I think I could have done this easier. I'm looking back at what I have. If I would have just right away on both sides used 10 as my base and these as my exponents, I could have gotten to that point a lot quicker right here. And then x plus 9 is equal to 2x minus 7, and from there I'd solve it the same way. So there's more than one way to do these problems. You might not always choose the shortest way first, but you should get the same answer no matter which way, even if you do it the long way or if you do it the short way. And on those earlier problems, remember there was 2 methods to use, so you can use sometimes one method works and sometimes either method works. All right, thank you very much. Have a wonderful day, and let me know if you have any questions.